Game begin.
Good morning, everybody. Thank you for coming to this talk. I work at a Canadian company called DNA Stack, where we've built a cloud platform for genomics, but I'm here today to talk about Java and reactive programming. So let me start by saying that reactive programming is pretty great. But what I don't like about it is that it became a buzzword. It's often described as this completely new paradigm that's going to magically solve all your performance problems, whereas in reality, it's not new. As a methodology, it's a collection of principles that have been around for a very long time. And even as a technology, it's built on top of other technologies that we've had for a while. And yeah, I think this aspect is often overlooked, which makes reactive programming sound even more magical. And that's kind of the context that I want to focus on in the next 40 minutes or so. So I'm going to go over the building blocks for reactive programming in the JDK. And I'm going to take you through what I call the 8 levels of reactive programming, which correspond to the features in the JDK in the order they were added to Java, and also in the order they make your system more and more advanced. But before we get to that, let me start by clarifying what it means to be reactive. Reactive refers to the ability of the system to respond to events as they happen. So it's basically a cool name for a collection of practices that allow us to build systems that are responsive. And in order to be responsive, we need to be elastic. We need to be able to handle varying loads and various numbers of users. And we need to be resilient to failures. We need to be able to contain failures. And it's OK to throw errors, but we need to be able to deal with them efficiently. And it turns out that a very good approach to becoming elastic and resilient is actually being message-driven, in particular, asynchronous messaging. So these 4 properties, responsive, elastic, resilient, and message-driven, this is really the foundation of reactive programming. Now, before we go any further, there's one thing you should know about me. I'm bad at making slides. So I've prepared exactly 4 slides for you today. This is one of them. And this is another one of them. And as this slide suggests, the rest of this talk is going to be pretty much a live demo. I like learning through examples, and I'm going to write a lot of them throughout this session. I'm going to write them in JShell, which is Java's implementation of a REPL that we've had since version 9. Don't worry if you haven't seen it before. It's actually very easy to figure out. So let me just switch to my JShell here. So on our journey through the history and levels of reactive, let's start really far in the past. Let's start with the very first version of Java, Java 1. OK? Reactive programming is basically a particular take on parallelism. And since the very beginning of Java, we've had some constructs for parallelism in the JDK. Namely, we had the runnable interface and its implementation thread. And that was a big deal at the time, right? We had this abstraction. We no longer had to write native code to handle threads, which was very cool. So basically, what we could do with Java 1 is something like this. I could create a new thread and give it a runnable to execute, let's say, something like this. I'm just going to print out the string, hello DevFest, and let's call this T. And now I can start a thread, and you can see that it executes correctly. And that's very nice, but it was pretty much all we could do with threads at the time. There was some advanced functionality like grouping, etc., but we were lacking really any sort of coordination mechanism between threads. So I'm going to call this level 0 reactive. If we're using threads, we're parallelized, which is a necessary first step towards reactive, but we're actually really far from a reactive system. And you shouldn't try to build a reactive system on top of threads directly. You know, it's a very low-level primitive. They're very heavyweight, and there's simply too much stuff that you would have to build yourself. But it is a start. Things got a bit more real with Java 5, though. Java 5 introduced executor services, callables, and futures. Executor service is basically a framework for task execution. So in practice, we're talking thread pools. It's typically used for executing runnables. Callable is similar to runnable in that it's an interface representing a task, but callables can return values, and they can throw exceptions. And futures are basically future results of asynchronous computations. So this is how they work together. I can create a new executor service. Let's say just a single threaded one. Don't need anything more complicated for this example. Let's call this E. And then I can submit a task, which is a callable here. So I'm just going to say something like this. Hello, DevFest. And this returns a future. Let's call this f. So you can see that this returns immediately, and the future is not completed, which basically means that it's asynchronous. Of course, it completes very quickly. If we take a look here, you can see that it's already completed. And if we try to obtain the value, you can see that it contains the correct value. So these three constructs actually give you quite a sophisticated asynchronous system. And I'm going to call this level 1 reactive, right? It goes beyond simple parallelization now. We have asynchronous computation, which is what reactive is all about. But futures are still too low level of a construct. They're hard to compose. What you typically see in practice, when people try to coordinate multiple futures, they do this sort of busy waiting. You have a group of futures, and you iterate over them, and you keep checking, is this done? Is this done? Is this done? And then when they're all done, you schedule a new task, which means that you're blocking on your main thread. Also, the get call that we executed here is actually a blocking call. So you can execute things asynchronously, but then to obtain the result, you need to do a blocking call. And being non-blocking is really a core part of being reactive. This is really how reactive is different from asynchronous. So from reactive perspective, it's very important to avoid blocking threads. We want to optimize our use of CPU, and avoid changing threads. Because changing threads means that the CPU needs to load data, and we want to optimize our use of cache. So that's how far your reactive system needs to go to become truly reactive. This really got easier with Java 7. Java 7 introduced the fork join framework, most notably fork join pool. Fork join pool is basically an implementation of executor service, so it is a thread pool. And it's an ideal candidate for writing asynchronous systems. It understands that some tasks need to wait for others. It avoids changing threads unless it's absolutely necessary. And it can help prevent cache corruption. So basically, it provides better utilization of resources and generally better performance for synchronous processing. The key assumption behind the fork join pool is that newly created tasks are more likely to have data in a closer cache. So maybe you should execute them on the same CPU, right? And maybe you should offload the older tasks to other CPUs. So in practice, when I create a task, it goes to the queue. Every thread has its own queue, and it keeps processing a task. When the thread is done, it says, hey, I'm done here. Do we have anything else in the queue? And it takes the next task. And if a task needs to do more work, it schedules more tasks in the current local queue, right? So how do we scale this across threads? Well, if you have multiple threads and a particular thread is done with its work, it performs what's called work stealing. So it basically takes a task from the bottom of someone else's queue. So again, it's the idea that I'm going to take something from the bottom of the queue because that's likely to have the least performance impact as I move it to another CPU. And it turns out that this actually works really well for asynchronous computations. We get really good single-threaded performance, and we get pretty good performance as we're switching threads. In fact, the fork join pool works so well that pretty much all other components in the JDK that have anything to do with reactive programming use fork join pool behind the scenes. So we wanted to use it directly. A very simple way of doing that would be just by modifying the example that we had before. So as I'm constructing my executor service, I can just say, instead of this single-threaded executor, give me fork join pool, and for example, common pool, and then I can still submit the task and extract the value from the future, and everything works. This is a very primitive way of using the fork join pool. I'm not really benefiting from it here, but it's just for demonstration purposes. So we have really good performance for synchronous programming now, and that's very crucial for a reactive system. So I'm going to call this level 2 reactive, right? With futures, with asynchronous, with fork join pool, we can do asynchronous very effectively. But there are still several building blocks that we'll have to build ourselves to have a fully reactive system. The main problems that we have right now is that we're still blocking on the main thread with futures. We still have the get call that's blocking, and our callables are hard to compose. But as it turns out, Java 8 helps us with this quite a lot by introducing completable future. Completable future is basically a framework for primarily non-blocking asynchronous computation. So it's built around this class called completable future, which, as the name suggests, is a future that can be explicitly completed. So you can set its value and the status. And when I say it's a future, I mean it literally implements the future interface, as we've seen right now. It also implements an interface called completion stage, which is something that was also introduced in Java 8. And that interface provides a representation for a stage in a computation. So basically, we use completable futures to model a task in a bigger workflow consisting of many tasks, primarily asynchronous tasks. And we have APIs for creating dependencies between them and chaining them together. So in other words, completable future addresses several problems we had with standard futures. It allows us to do non-blocking computation. It makes tasks easy to compose. And it automatically uses fork join pool behind the scenes. So it performs very well. Pretty amazing, right? So how does this work? Well, the basic API is pretty simple. I can create a new completable future, let's say of type string, and let's call this CF, and then I can complete it. Say done. And now if I call the get method, it's actually going to return the value that it was completed with. So what happens if I don't complete it? Well, let me just reset here and just call the get method directly. And you can see that nothing happens, right? This is the blocking call from the future interface. And it's going to keep blocking until somebody else completes the future. That's how you sort of synchronize things with this construct. Aside from completing the future normally, I can also complete it exceptionally. I can call complete exceptionally here, which takes a throwable. So I can just give it, let's say, new illegal state exception. And now if I try to extract the value, it's actually going to fail with the exception that I gave it. So that's sort of the basic functionality. You can complete futures normally and exceptionally. But so far, we're not really seeing the benefits for reactive programming, are we? So what else can we do with this? Well, quite a lot, actually. Completable future is a big class, and it has quite a few methods and quite a few public ones. There's 52 of them, if I remember correctly, and that's without overloading. A few of them comes from the future interface, as we've seen, but the vast majority of them come from the completion stage interface, which has a whopping 38 methods. So yeah, probably not the best design, but it's actually not as bad as you might think. Basically, the reason we have so many methods is because there are kind of 3 categories of things that we're trying to express here, and we want to capture all the possible combinations across these 3 categories, which gives us 36 methods. So the 3 categories are, what kind of a task is this? What kind of an operation it supports? And where does it execute? Okay. As for the task, there are 3 types. It can be a runnable, it can be a consumer, or it can be a function, which correspond to the respective functional interfaces. As for the operation, we can chain them, which means execute one after the other. We can compose them, as in function composition, or we can combine 2 tasks into one using AND or. And as for where to execute it, we can basically tell it to execute in the same executor as the caller, or we can let the fork join pool decide, or we can explicitly give it an executor. So for example, I can take a look at the method then run here. And you can see that this method starts with then, which implies chaining. Then it says run, which implies it's going to take a runnable. And then you can see we have 2 versions of this. We have then run and then run async. So the first one is obviously execute in the thread of the caller. The next one is actually overloaded. And there's a version where you explicitly tell it where to execute, or you let the fork join pool decide. So you get the idea, right? You're kind of combining all these things. So I'm obviously not going to show all these methods, but there are 3 basic patterns that you use with completable futures to model workflows. And the first pattern is asynchronous sequencing. So asynchronous sequencing is basically about creating the basic dependency, ensuring that one task runs after another. So let me demonstrate. And this time, I will create the futures in a different way that's a bit more realistic usage, and we'll do everything in a single pipeline. So I can start by saying completable future supply, and I'm going to do everything asynchronously, so I'm going to use supply async, which takes a supplier, of course, and I can just say, OK, let's just return hello. Then I can call then apply. Actually, let's do then apply async. I promise to do everything asynchronously, which takes a function. So I can, for example, say, OK, here's a quick lambda. Concatenate this string with some other string, right? Something like this. And then I can call then accept, which takes a consumer. So I can just say, OK, just print whatever you have. And if we run this, you can see that I actually printed the string that I had here. So this is a very simple asynchronous sequencing pipeline. And you can kind of see the key property of completable future API here. Everything here returns a completable future, or almost everything. So you kind of get this nice fluent API where you can chain things and you can model workflows very nicely. The second common pattern is a synchronous join. So I have these two things that I ran, and I want to combine them into one. So it's kind of like merging two branches in your workflow. So let's demonstrate this very quickly. I'm going to keep the original completable future. I'm going to change then apply async to then combine. Or actually, let's do combine async again. And this takes another completable future that I'm combining with, and then it takes a by function. So OK, let's start with the first one. Completable future, again, create asynchronously. Let's use our favorite testing string here, just like this, and then a by function. So I'm going to use two parameters here, and I'm just going to combine them, just like this. And you can see that this works the same way, but now we have a very simple workflow, right? I have two tasks, and then I combine them into one. So that's a very simple asynchronous join pipeline. And the third pattern is recovering from failures. And this is very relevant for us, because staying responsive when you encounter a failure and isolating failures, dealing with them efficiently, is a very core part of a reactive system. So with completable futures, if you have a failure and you chain tasks together, the failure actually blocks the rest of operations from happening, and you get a failure at the end, which is actually very nice. You can sort of set up a bunch of tasks executing in different threads, and you can deal with the error at the end in the thread that you care about. So let's take a look at what an error handling scenario could look like. There are several ways of handling failures in the completable future framework, but the main one is really the method exceptionally. So I'm just going to add that here. I'm going to say exceptionally, and this takes a function on a throwable. So I'm just going to say, OK, maybe let's acknowledge an error. That's the best error handling, right? And then I'm going to say, OK, give me the message from the error. Everything else can stay the same. And this actually completes just fine, because nothing failed here, right? But let's try to fail one of them. So I'm going to keep one task completing successfully. I'm going to fail the other one. Then I'm going to merge them. The failure is going to propagate. And then I'm going to deal with it at the end. So I can keep the original future here. And I'm going to change the other one. Let's just create a failed future, just like this, which takes a throwable. So I can give it new illegal state exception, for example. And now we can see that the failure propagated, but we did actually handle it correctly. So that's the basic failure recovery pattern. Basically, you always want to have exceptionally at the end of your pipeline. So with completable futures, Java 8 gives you a pretty powerful framework, right? But as you start using it, you realize that there are still a few things missing in it. And that's actually largely addressed by Java 9. So what was added in Java 9? Well, quite a few methods, actually. I would classify most of them as utility methods. There are a few factory methods and a few methods that makes it easier for you to subclass completable futures, should you ever need that, but you almost certainly won't. So these are not too exciting. But there are three methods that I'm very excited about. Java 9 basically introduced a new way of completing completable futures based on a timeout. So in Java 9, I can create a new completable future. Let's use just strings again. And let's call this CF. And now I can call complete on timeout, which takes a value, in my case, a string, say timed out, and then it takes the actual timeout, let's say 5 seconds. So now if I call get, what's happening here is the completable feature is going to wait for 5 seconds to see if anyone completes it. And if nobody does, it's going to be completed automatically with the value that we gave it, right? So you can complete features successfully based on a timeout. You can also complete them exceptionally based on a timeout. You know, if I just reset here, I can call the method or timeout, which just takes the actual timeout. So let's say 5 seconds again. And now, if I call get, it's going to wait for 5 seconds, see if anybody completes it. And if nobody does, it's going to fail with a timeout exception. OK, so we can complete features normally based on a timeout, but also exceptionally based on a timeout. And that's actually pretty cool. I'm sure you can imagine how this is useful. If you have sort of a microservice architecture where you have a service talking to other services, you would basically want to have timeouts in place, right? The third method that I'm excited about is the method copy. And the method copy returns a defensive copy of a completable feature. And this might not immediately be obvious why this is so useful, but it was the crucial missing piece for creating asynchronous APIs. And when I say asynchronous APIs, I mean APIs that return completable features. And basically, in those cases, you want to pass completable features to your clients, right? You want them to be able to chain actions onto them and create dependencies. But you don't want them to complete your completable feature, the feature that you're using internally behind your API, right? So you're trying to provide this sort of one-way synchronization. You want them to be able to read. You don't want them to be able to write. And that's exactly what the method copy allows you to do. So let me demonstrate this real quick. I'm going to create a new completable feature, and then I'm going to create copy. Let's call this copy. And now, if I complete the original, you can see that the original is, of course, completed. But the copy is actually completed as well. And if I try to extract the value from the copy, it's going to be the value that the original was completed with, right? So I can give this to my clients, and the clients can chain actions onto this. So what happens if I do this the other way around? Well, let's try. I'm going to reset the original. I'm going to reset the copy, and then I can complete the copy. And of course, copy is now completed, but the original is not completed, right? So the clients cannot write back. So this whole completable feature thing, I'm going to call this level 3 reactive. This actually gets us pretty far. You can absolutely build a fully reactive system on top of this, and it's going to work nicely. Completable features address a bunch of issues we had with features. We can compose them easily. We don't have to block on the main thread to coordinate. You can just say, execute this task when this other task is done. We don't need to make blocking calls to get the value. We've done this a bunch of times just because it was easy, but you've seen that there are other methods to do this asynchronously. And notice that we didn't see any executor services, thread management, etc. That's all abstracted from. It's hidden behind the scenes. So completable features are actually not that low level. They're a pretty powerful tool for building reactive. So what are we missing then? Well, so far, we've been executing workflows on individual objects, right? Individual pieces of data. It would be nice if we could deal with live data, with streams of data as it's coming in. And you can try implementing this with completable features, and you might be pretty successful. But very likely, pretty quickly, you're going to run into problems. For example, you might realize that the producer of your data might be faster than your consumer, and you need to deal with that, right? So what can you do? Well, you can drop the data. That's obviously not great. You can block. That's obviously not very reactive. You can maybe buffer it, but eventually you will run out of buffers, and you need to deal with that. Or you can implement some sort of a back pressure. And that brings us to reactive streams. Reactive streams are a de facto standard for asynchronous stream processing with non-blocking back pressure. So basically, this concept of back pressure comes from the metaphor of a water pipe. If you're a consumer of water at the end of the pipe and you're getting too much water, you can adjust the valve, you can adjust the tap, and that reduces the load on you, but it creates the pressure back to the source, right? And this notion of backpressure is really an integral part of the reactive streams framework because it allows our message queues to be bounded. And that's very important if you have finite resources. Java supports reactive streams through the Flow API introduced in Java 9. And the Flow API consists of two classes. There's the class Flow, and there's a class Submission Publisher. The class Flow contains 4 nested static interfaces, which correspond to the basic reactive streams concepts. You have a publisher, which produces data. You have a subscriber, which consumes messages from the publisher. You have a subscription, which is the link between the publisher and the subscriber, and that's what's used to implement backpressure. And then you have a processor, which is both a subscriber and a publisher. And these are useful as kind of intermediate stages in your computation. They can sit on the flow somewhere between the publisher and the subscriber and perform transformations. And the other class, Submission Publisher, is basically an implementation of the publisher interface from the Flow class. So let's implement a simple flow in which we have a publisher sending messages, and we have a subscriber consuming messages one at a time. Very simple. So let's start with the subscriber. I'm going to create a class. Let's call it simple subscriber. And this is going to implement the subscriber interface. Let's say subscriber of type string, just like this. And now we need to implement all the methods in the subscriber interface. And there are 4 of them. There is a method onSubscribe, so public void onSubscribe, which actually takes a subscription. Let's call this sub. And this is basically the first method that's called on the subscriber. So this is called when you register a subscriber with the publisher. It receives the subscription, which is used to control the flow of messages between the two. So a subscriber can make a request for more data, or it can request that no more data is sent. The next method here is the method onNext. So again, public void onNext. We're basically implementing all the callbacks in the subscriber now. And this takes a message. In our case, a message is a string. Method onNext is basically called whenever the publisher publishes a message. So this is how we're handling messages. Then you have a method called onError, public void onError, which takes a throwable. And this is the last method that's called on the subscriber. It's basically called whenever a publisher or the subscription encounter an error that they cannot recover from. So you have a guarantee that no other methods on the subscriber will be called after this. This is an error that you really cannot recover from. And similarly, you have the method onComplete, public void onComplete, which actually doesn't take any arguments. And it's similar in a way that it is the last method called. It's called when the publisher is closed. So again, no other messages will be coming after this for the given subscription. So let's try to close everything and compile this and see if I didn't make any typos. This is looking good. OK, so let's try to actually implement these methods and see how that works. So what do we have here? OK, well, first, I'm going to need a subscription, right? So let's create a private subscription field. Let's call it sub, and then implement onSubscribe. So in onSubscribe, what I definitely want to do is set this subscription, this sub equals sub, and then I want to request the first message, just like this, right? So the subscription actually has 2 methods. There's a request method, which basically adds data to the current unfulfilled demand. And if you just give it sort of a standard number, it basically says, OK, the subscriber might receive up to this number of onNext calls. Up to this number, because the publisher might be closed in the meantime. So you basically use the request method to implement backpressure, right? This is what backpressure is about. The other method is the method cancel, which is a signal that the subscriber can send to the publisher, basically saying, OK, I don't want any more messages. This is sort of best effort, so you might receive more messages afterwards, but you're just aiming not to. There are a couple of sort of edge cases. For example, if you give 0 or a negative number to the request method, it's basically going to fail with an illegal argument exception, so the onError method on the subscriber is going to be called. Similarly, if you give it max value, as in long max value, it basically says unbounded number of invocations. OK, so that's on subscribe. What do we need to do in onNext? Well, let's print the message we've received. So I'm going to print something like this. Let's say received, and then the actual item. And then let's request another message. OK, then onError. Well, in onError, I need to handle the error. So I'm going to implement the best error handling. I'm going to say print stack trace. This should be enough. And then finally, onComplete. Well, in onComplete, I need to clean up. In our case, we don't really have anything, so all I'm going to do is actually print out that we're done. And let's see if this compiles. And it doesn't. OK. Oh, yeah. Of course, typo at the end. Let's try now. All right. That wasn't too bad. Let's try to create this subscriber, actually, see if that works. Let's call this sub. OK. This is looking good. So now to test this, let's create a simple publisher. And this will actually be much easier because, like I said, JDK already provides an implementation called the submission publisher. And it's kind of meant as a base implementation of your own publisher. But it actually provides everything we need for this simple use case, so we can just use it directly. So all I'm going to do here is create a new submission publisher. Again, I need to tell it it's of type string. And let's call this pub. Submission publisher has a bunch of methods, but the publisher interface actually only prescribes one. And that method is subscribe. So subscribe means register this subscriber with the publisher. So let's try that. Let's try to register our subscriber. This is looking good. So let's see if this actually went through. Let's call get subscribers. And yes, there is something. All right, so let's try to actually submit a message. Let's say our favorite string. And you can see that this went through. And the subscriber actually received the message. And we can try this a bunch of times. It's going to go through pretty reliably. So now, when we're done, we can close the publisher, and we can see that our subscriber cleaned up as well. It's printed done. And now, of course, if I try to submit more messages, it's not going to go through because everything is closed. Right? So this gives us a simple reactive streams publish-subscribe system. It's actually a bit more sophisticated than you might think, particularly because the built-in publisher is actually pretty smart. It uses fork join pull underneath to deliver messages asynchronously to the subscribers. It uses completable futures. It provides some buffering, error handling, that sort of thing. So it's actually not that simple. Having said that, you should never implement your reactive system like this. What we have in Java right now, it's an SPI. It's not something that's meant to be implemented by application developers. It's something that's meant to be implemented by people developing reactive streams frameworks. So don't do this yourself. There's a bunch of corner cases that you would need to handle. Just use the library. So I'm going to call this level 4 reactive, right? We're pretty close to a fully working reactive model, but still not quite there because we don't have the implementation in the JDK. We still have to do it ourselves. So where can we go from here? Well, we've seen a nice reactive model that works for passing messages in an asynchronous and non-blocking way with streams and backpressure between threads in the context of a single JVM, right? But a true reactive system needs to be resilient. So it typically consists of multiple services typically communicating over HTTP. Which brings us to Java 11, which introduced an HTTP2 client. So the new HTTP2 client is basically a replacement for the old HTTP role connection API. And it supports all the cool new things. It supports HTTP2, WebSockets, including TLS, server push, proxies, cookies, authentication, all things like that. I'm going to credit this to Java 11 which is when this became a stable part of the JDK. But it has been available since Java 9 as an incubator module. It actually changed quite a bit. So to demonstrate a client, I'm going to need a server. And if there's anything that I've learned from doing live coding at conferences, is that you can never rely on the internet at these conferences. So I'm going to create a very simple server here. And it's going to be really simple using really old APIs in Java. I'm basically going to create a server that has a single endpoint. And no matter what request I send to this endpoint, it's going to respond with a fixed string, right? So let's do this very quickly. I'm going to start with an HTTP handler. Let's call this handler. And this is going to be a quick lambda. Actually, not that quick. It's going to be a multi-line lambda, where we define our string. Let's say our favorite, hello DevFest. Then I'm going to set the response headers. I'm always going to respond with 200. Everything is OK. And I will attach the length of my string. And then finally, I'm going to open an output stream, attach my response body, get response body. And here, I'm going to use the output stream to write my string to the actual response. And this is an old API, so I actually need to do this through get bytes, just like this. And let's try and close everything. It looks like this compiled. OK, so let's create the actual server. I'm going to create a server here, and this needs a port. So I'm going to say, let's say 8000. Don't need a backlog. Let's call this HS. And then I can create my endpoint. Let's say /hello, and I will attach my favorite handler to this endpoint. And finally, I can start the server. And now hopefully this is working, but to test it, we're going to need a client. So let's focus on the new functionality in Java 11 now. So this client API is built around 3 main classes. There's HTTP client, HTTP request, and HTTP response, which are pretty self-explanatory. So I can start by creating the client, HTTP client, new HTTP client. Let's call this HC. I can just quickly check here. This indeed supports HTTP2, even though I'm not really taking advantage of it in this example. Then I can create the request, which actually uses a builder API. So I can just give it a URI. And the URI to my server was HTTP localhost. I think I used 8000 /hello, just like this. Then let's do a GET request. And let's call build, and let's call this a request. And now I can use the client to send the request to my server. And this also needs something called body handler here. And in this case, I'm not going to worry about this. I'm just going to tell it to treat everything as strings. That's good enough for my use case. And let's call this response. So now to check if this works, let's see. Status code 200. This is looking promising. Let's check the body. Hello, DevFest. OK, our client and our server are working just fine. But of course, this is a synchronous call over HTTP, right? Which is not great for reactive. But the client is very flexible. If I wanted to make this asynchronous, I only need to change one thing. All I need to do is change the send to send async, which now, of course, is going to return a completable future, but it's going to work the same. I can just extract the body, and now we have a fully functioning HTTP2 call. So now we have asynchronous calls over HTTP2. We can use reactive streams and completable futures on each end. And in fact, the HTTP2 client actually uses the reactive streams model and completable futures underneath. And yeah, it's just pretty nice. So let's call this level 5 reactive. Should you build your reactive system with these constructs? No, it's still too much work. You're probably still better off using some sort of framework built on top of the JDK. So what should you do? What is beyond level 5? Well, there are a couple of things missing in the reactive streams API in Java that you would most likely need in your real-life system. You're missing things like operators, even really basic ones, like map or filter. You don't have things, like dealing with cycles, restarting, monitoring, tracing, that sort of thing. And that's all hard to do. But thankfully, there are libraries and systems out there that do this for us. So I would say that level 6 reactive is using a proper reactive streams library. And there are a few good ones for Java. The most well-known ones are RxJava and Reactor. They're both very good, very mature, tested in production, and supported by large companies. And they do a very good job when you're passing things between threads. But again, it's in the context of a single JVM. So if you want to take this even further and go to level 7 reactive, you're probably still better off using a full distributed reactive system, such as Vertex, which actually uses RxJava, or maybe Spring 5, which relies on Project Reactor. And you can connect your services to distributed messaging system, maybe something like Kafka. So you can see a clear trend here with reactive programming in Java, right? More things are moving from the responsibilities of reactive streams developers to the actual JDK. And we're currently on level 5 with the JDK, but you can see that the basic building blocks are there, but there's still a couple of things missing. So that's it from me. If you have any questions, I believe I have office hours starting right after the break at 11, so just come by and say hi. And since I didn't bring any slides, I will export my JShell session and post it to Twitter if you want to come back to these examples. Here's my Twitter handle. And otherwise, thank you. I hope you found this interesting, and enjoy the rest of the conference.